Welcome back, my dear students. Last class we have discussed up to finding the depth of neutral axis for a singly reinforced section according to limit state method of design. So today's class we are going to discuss the moment of resistance of a section. Moment of resistance of a section, it is denoted as MOR, or simply ultimate moment MU. So before understanding this, you need to understand what is the difference between the moment of resistance, or what is the basic concept of moment of resistance and bending moment. So first we will discuss what is bending moment. What do you mean by bending moment? If I am considering a simply supported beam, with UDL having W kilonewton per meter as the load, having a span of L meters. So if I'm taking this reaction R1 and this is R2, this is W L by 2, this is W L by 2. Now if I draw the bending moment diagram, I'll get the bending moment diagram. I'll get the bending moment like this, with the maximum value as W L square by 8. And I'm considering a section, at a distance x from here, x from this support. I'm considering a section distance x from the support. Then the bending moment I'm considering a section xx. Then the bending moment at xx, I could write it as R1 into x minus W x square by 2, and the maximum bending moment maximum, I could write it as W L square by 8. From this you will understand the bending moment means what? It is the actual moment developed in a section due to given value of load. It changes from point to point, isn't it? So I could say the bending moment is the actual moment developed in a section due to the given value of load. It changes from point to point. That is, at section xx, the value is R1x minus Wx square by 2, which means as the value of x varies, the bending moment value at any section also varies. And the maximum bending moment value is WL square by 8 for a simply supported beam having W kilonewton per meter as the load. Now coming to the moment of resistance. Moment of resistance simply means it is the maximum capacity of a section to resist the bending moment. That is, the maximum capacity of a section to resist the bending moment is called as the moment of resistance of a section. At this moment of resistance, any one material, either concrete or steel or both, shall be at its maximum permissible stress value. That is, I can write the moment of resistance of a section. is the maximum capacity of a section to resist the bending moment. That is, for a particular section, the moment of resistance will always be fixed based on the dimension and the area of steel provided. The moment of resistance of a section will always be fixed. At moment of resistance, any one material, either concrete or steel or both, shall be at maximum permissible stress value. That is, this moment of resistance will always be dependent on the dimension, that is your breadth and depth of the section, as well as the area of steel provided. That is, for a particular section, this moment of resistance will be a constant value. That is, I could summarize the moment of resistance of a section as, that is, in equilibrium, the total force of compression must be equal to the total force of tension. The applied bending moment at collapse, that is the factored bending moment, is equal to the resisting moment of the section provided by internal stresses. This resisting moment is called as the ultimate moment of resistance, or simply moment of resistance. Now, if you see the stress strain diagram for a singly reinforced section, you could see the tensile force, that is 0.87 FyAST. The 0.87 FyAST is acting here, and the compressive force, that is the total compressive force of 0.36 FCKBXU is acting here. And the distance between these two is what? D minus 0.42 XU, that is your lever arm. Here what is happening is, this force which are acting in opposite direction, that is the tensile force and the compressive force, will create a couple, that is the moment, the bending moment due to the applied load is resisted by the concrete, the compression the compressive force produced by the concrete and the tensile force produced by the steel, and they both produces a couple in the opposite direction of the moment created by your applied load, and that moment developed internally is called as your moment of resistance. So I could write the moment of resistance. I could write the moment of resistance is equal to either in terms of compressive force or either in terms of tensile force, that is the force into the perpendicular distance between the two forces. That is, I could write as the force into the perpendicular distance. Here the perpendicular distance is what? Lever arm. That is, I could write as, if I'm telling in terms of concrete, I could write as C into lever arm or T into lever arm. So if I am writing the moment of resistance with respect to concrete, I could write it as, concrete is taking compression, I could write it as moment of resistance is equal to C into, with respect to concrete, C into lever arm, that is C is what? 0.36 FCK B XU into lever arm is D minus 0.42 XU, D minus 0.42. That is, I could write the moment of resistance MOR or MU with respect to concrete as 0.36 FCK B XU into lever arm, that is D minus 0.42 XU. Similarly, with respect to steel, I could write the moment of resistance as T into lever arm. I could write as T into lever arm. Here what is T? T is the tensile force, that is 0.87 Fy AST into lever arm is D minus 0.42 XU, D minus 0.42 XU, D minus 0.42 XU, which means the moment of resistance, or MU with respect to steel or reinforcement, I could write it as 0.87 Fy AST into D minus 0.42 XU. Now, based on the attainment of the maximum strain in concrete or steel, I could classify this section into three based on the attainment of the maximum strain value. The first one is called as a limiting section. There are three cases. First one is limiting section or balance section, under reinforced section. Third one, over reinforced section. So based on the attainment of the maximum strain, there are three sections basically: limiting section or balance section, under reinforced section, and over reinforced section. So we will discuss in detail of the three sections. That is, first one we will discuss on the limiting section, or it is also called as the balance section. The first one we are going to discuss is the limiting section or balance section. A beam section is called as a balance section when the cross-sectional area of the steel bars provided as reinforcement is such that the maximum compressive strain in bending in concrete and the maximum strain in steel reaches simultaneously to their specified values. That is, the depth of the neutral axis at this time is maximum, and it is called as XU max or XU limit. While discussing XU limit or XU max, the limiting depth of neutral axis, I had told, when the strain in concrete and the strain in steel reaches its maximum simultaneously, then the section is called as a limiting section or balance section. That is, we will provide the reinforcement in such a way that the strain in steel and the strain in concrete reaches its maximum at the same time. So when I'm seeing the stress strain variation of a singly reinforced section, we will see like this. If I draw the strain variation, I could see the strain in concrete 0.0035 and the strain in steel, that is 002 plus 0.87 Fy by Es reaches its maximum value at the same time, then the depth of the neutral axis is called as XU limit or XU max, and this section and the corresponding section is called as limiting section. The corresponding section is called as a limiting section. So if I draw this stress diagram, now if I draw this stress diagram, I will get it like this. The stress diagram, it will be a straight line, then it will be parabolic. Acting at a distance of C, at a distance of 0.42 XU limit, and this value is 0.36 FCKB XU limit, and the tensile force T is equal to 0.87 Fy AST. And for a limiting section, the area of steel provided is such a way that the strain in concrete and the strain in steel reaches its maximum. Then that area of steel is denoted as AST limit, that is limiting section AST, that is area of steel for a limiting section, is denoted as AST limit. So I could write the tensile force as T is equal to 0.87 Fy AST, 0.87 Fy AST limit. I could write as 0.87 AST limit. Now the moment of resistance I could write as moment of resistance with respect to concrete. I could write as C into lever arm. What is lever arm here? Lever arm is the distance here, that is D minus 0.42 XU limit. So I could write it as moment of resistance for a limiting section is equal to 0.36 FCKB XU limit into lever arm, that is D minus 0.42 XU limit. And moment of resistance with respect to steel, I could write it as 0.87 Fy AST limit into D minus 0.42 XU limit. So this is the moment of resistance of a section, singly reinforced limiting section. Now consider this. And taking the moment of resistance of a balanced section with respect to concrete, I could write the moment of resistance as is equal to 0.36 FCKB XU limit into D minus 0.42 XU limit. You could denote it as XU limit or XU max, it's up to you. Both are same, that is neutral axis corresponding to a limiting section. And taking the D from this outside, that is I'll get it as 0.36 FCKB XU limit D into 1 minus 0.42 XU limit. Now I'm multiplying and dividing by D. I'll get this value as 0.36 FCKB XU limit by D into D square to 1 minus 0.42 XU limit by D. That is, I could rearrange it. I will rearrange it and like this, write like this: 0.36 XU limit by D into 1 minus 0.42 XU limit by D into FCKB D square. You could see here this value is a constant. And will depend only on the XU limit by D value, which in turn depends on the grade of steel being used. That is, I could write this as a constant. I'll denote it as Q. I'll denote this capital Q into FCKBD square, where Q is equal to 0.36 XU limit by D into 1 minus 0.42 XU limit by D. So this value depends only on the grade of steel being used. That is, for Fe250 grade steel, that is mild steel bar, if we substitute the value for XU limit by D as 0.53, that is for ms bar, Fi is equal to 250 Newton per mm square. XU limit or XU max by D is equal to 0.53. You will get the value for QS. 0.148. You get the value for QS 0.148. For HYSD bars having Fy 415 Newton per mm square, you have your XU limit by D as 0.48. You get the value for QS 0.138. And for HYSD bars having Fy 500 Newton per mm square and XU limit by D as 0.46, you will get QS 0.133. That is, the moment of resistance of a limiting section with respect to concrete, I could write it as MOR is equal to Q FCK BD square, where Q value depends on the grade of steel. That is, for MS bar it is 1.148, for HYSD bar having 415 grade it is 0.138, and for HYSD bar having grade 500 it is 0.133. So today's class we will wind up with this. Next class we will be discussing on the under reinforced section and the over reinforced section. That is the next two type of cases, and after that we will go for the numerical part, that is the analysis and design of a single reinforced section. Thank you.